Okay, let's unpack this. Today, we're taking a really fascinating journey, not through space, but back through time,
Hmm.
right down to the absolute basics, the fundamental building blocks of everything around us, the atom.
It's quite a story, actually.
We're basically tracing the history, aren't we?
Huh.
Looking at how we went from just, well, philosophical
It's sheer
ideas
speculation.
to actual measurable science,
Yeah,
chemical laws and all that.
exactly. Our sources today, they kind of lay out this historical roadmap of chemistry. We're looking at the whole lineage of the atom. So not just what it is, which we learn in school, but how did we even start talking about it, naming it? And this is crucial. How did we figure out how to weigh these tiny things?
And what gets me right away is the idea itself, this concept of a smallest indivisible piece of stuff.
Yeah.
It didn't just pop up in one place. Our sources say it emerged almost at the same time in two completely different ancient cultures, thousands of miles apart. It's kind of mind-blowing.
It really is. It shows that this question, what's the ultimate nature of matter? It's a fundamental human question. It cuts across cultures. So you look back to ancient India, maybe around 500 BC, you find this philosopher, Maharishi Kanad.
Cannot, right.
And he postulated that all matter, everything, must be made of tiny, ultimate particles, indivisible particles.
And he had a name for them.
He did. He called them Parmanu.
Parmanu, the ultimate particle. I like that.
And while Kanad is thinking about Parmanu in India, over in ancient Greece, you've got the philosopher Democritus, basically doing the same kind of thinking.
No way.
Yes, and he gives these indivisible bits of matter the name we still use today, atoms. From atomos, meaning uncuttable.
Atoms. So Parmanu and atoms. Same idea, different places, different times, roughly. Well, that's incredible.
It sets such a magnificent stage, doesn't it? This parallel quest born from pure logic, centuries before any kind of lab equipment existed. But, moving from just the idea of an atom, a philosophical concept, to a science you can actually use, something predictive.
Yeah, that's a big jump.
That required rules, hard, verifiable rules.
Exactly. And this is where the story jumps forward quite a bit, almost 2,000 years, actually.
Right.
To the person who really, you could say, flipped the switch for chemistry as a science, Anton Lavoisier.
Ah, Lavoisier, the architect.
He's often credited with laying the very foundations,
Yeah.
establishing that chemical reactions aren't some kind of magic.
No, they follow rules, mathematical rules.
What was his big contribution then, according to our sources?
Well, Lavoisier's genius was in realizing and proving that chemistry happens in a closed system. His first huge law was the law of conservation of mass.
Okay, conservation of mass, what does that mean, basically?
It's quite simple, but revolutionary for its time. Mass can't be created or destroyed in a chemical reaction.
So what you start with, you end with, weight-wise.
Precisely. If you start an experiment with, say, 10 grams of stuff, you'll end with 10 grams of stuff, even if it looks completely different. Gas, liquid, solid, whatever. The total mass stays the same.
That makes sense. It makes experiments repeatable, testable.
Absolutely. It grounds chemistry in measurement. But, just knowing mass is conserved isn't quite enough.
How so?
Well, think about it. If I analyze table salt today and you analyze it next week, we need to get the same results right. Otherwise, it's not reliable.
Consistency.
Right, exactly. And that brings us to another key figure, Joseph L. Proust.
Proust, okay, what did he add?
Proust gave us consistency, his law of constant proportions. It states that in any given chemical substance, the elements that make it up are always present in the exact same proportions by mass. Always.
Always the same recipe, basically.
That's a great way to put it. It doesn't matter if you get the substance from France or India or Mars. The recipe, the mass ratio of its elements, is fixed.
Okay, can we make that concrete, like with an example?
Sure. The classic example is water, H2O. Everyone knows water.
Right.
Our sources confirm the ratio by mass of hydrogen to oxygen in water is always 1 to 8. 1 part hydrogen for every 8 parts oxygen by mass.
Always 1 to 8, no matter what.
No matter what. That fixed, reliable ratio is what turns chemistry from observation into a predictable industrial science.
So we have these two big laws now. Conservation of mass from Lavoisier, constant proportions from Proust, foundational stuff.
Rock-solid foundations. And it's these two laws, this experimental proof, that directly leads to the next giant leap.
Which is?
John Dalton.
Dalton, the atomic theory guy.
The very same. Dalton was the scientist who brilliantly took these experimental laws and built the first really comprehensive atomic theory on top of them.
So Dalton wasn't just reviving the old Greek idea of atoms randomly, he was connecting the dots.
Precisely. He wasn't just philosophizing. He looked at the evidence from Lavoisier and Proust and said, the only way these laws make sense is if matter is made of tiny, fundamental particles.
A true unifying theory, then, linking the ancient Parmanu and atom idea to the modern math of chemistry.
Absolutely. And his theory had specific points, postulates. Key among them were, all matter is made of these tiny particles called atoms. That's postulate 1.
Okay, basic building blocks.
And crucially, postulate 2, essentially. Atoms of different elements are fundamentally different. They have different masses, different chemical properties.
That explains why, lead feels heavy and helium feels light. They're made of different types of atoms with different inherent properties.
Exactly.
But wait, you said his theory was based on the laws. How did those laws lead to specific postulates? Like, which part of the theory came directly from, say, Lavoisier's law?
Excellent question. The theory had to respect the laws. So the postulate that comes directly from the law of conservation of mass is this one. Atoms are indivisible particles, which cannot be created or destroyed in a chemical reaction.
Ah, I see. If atoms themselves can't be destroyed or created, only rearranged.
Then the total mass has to stay the same. It fits perfectly. Lavoisier's law demands indivisible, indestructible atoms, at least within chemical reactions.
It's really elegant when you see how it fits together.
It is. But it's also important to remember what Dalton didn't know. History has limits, right?
Sure. What's the key thing he missed, based on our sources?
Well, one statement that is definitely not part of Dalton's original theory is the idea that atoms themselves are made up of still smaller particles.
Ah, so no electrons, protons, neutrons in his picture.
Not at all. For Dalton, the atom was truly the end of the line, the indivisible fundamental unit. We know better now, of course, but for his time, it was a monumental framework.
Incredible how much they built just on those two laws, really.
It truly is. Okay, so we had the theory. Matter is atoms. Atoms follow rules. But now science needs to get practical. How do we talk about these different atoms? How do we measure them conveniently?
Right, the language and the toolkit of chemistry.
Exactly. If you've got different elements, different atoms, you need a shorthand, a universal way to refer to them.
Dalton actually started that, didn't he, using symbols?
He did. Dalton was the first scientist our sources mention who used symbols for elements in a very specific, systematic way, though his were a bit pictorial, circles with dots and lines.
Maybe not the easiest to jot down quickly in a lab notebook.
Probably not. The much more practical, elegant system we use today, the 1 or 2 letter symbols like H for hydrogen, O for oxygen, Phi for iron.
Yeah, the standard periodic table symbols.
That system was suggested by Berzelius, much cleaner, much more universal.
Then who makes sure everyone sticks to the system? Like, if someone discovers a new element, who decides the name and symbol?
Ah, the gatekeepers. That role falls to IUPAC.
IUPAC.
The International Union of Pure and Applied Chemistry. They are the global body that approves the official names of elements, their symbols, the units we use. Basically, they maintain the rulebook for chemical language.
Keeping everyone on the same page. That makes sense.
And sometimes those symbols have neat historical links. You mentioned Phi for iron.
Yeah, why Phi, not ERR or something?
Because it comes from its old Latin name, fair. IUPAC often respects those historical roots.
Ferrum. Okay,
Yeah.
Cool little detail. Now, what about measuring these things? You said atoms are different masses, but they're tiny. How do we even weigh them?
Yeah, they are incredibly small. Atomic radius, for instance, is usually measured in nanometers, billionths of a meter.
Nanometers. Tiny. So weighing them must have been a challenge.
A huge challenge. For a long time, scientists just used relative weights, comparing everything to the lightest element, hydrogen, or later, oxygen.
But that wasn't ideal.
Not entirely consistent. So in 1961, the scientific community agreed on a single, stable, easily measured standard, the carbon-12 isotope.
Carbon-12, why that specific one? Why not stick with hydrogen, the simplest?
Good question. Carbon-12 is very common, it's stable, and its mass could be determined very precisely. It provided a really solid benchmark, and based on that benchmark, they could define the standard unit of atomic mass, the atomic mass unit, or U.
Okay, so what is 1U?
By definition, one atomic mass unit is exactly 1/12th the mass of a single atom of carbon-12.
1/12 the mass of a carbon-12 atom.
Got it.
So everything else, hydrogen, oxygen, iron, their atomic masses are measured relative to that standard.
Exactly. It gives us a precise universal scale.
Okay, so we've named them, symbolized them, and figured out a standard way to weigh them. What's next in building up chemistry?
Combining them. If atoms are the letters, now we need to make words and sentences. We need to build compounds.
Right. So what's the basic word in chemistry?
That would be the molecule. A molecule is the smallest particle of an element or a compound that can exist independently and still show all the properties of that substance. Like a single H0 molecule still behaves like water.
Makes sense. And how do we know how many atoms are in a molecule? Like H0 has 3 atoms. Is there a term for that?
Yes, that's called its atomicity, the number of atoms in one molecule.
Atomicity. Simple enough.
So water is triatomic. Oxygen gas, O0, is diatomic. Some can be more complex. Our sources mention phosphorus, for instance. A single phosphorus molecule is actually tetraatomic. P.
PO. 4 phosphorus atoms sticking together. Okay, but how do they stick together? Why does oxygen grab 2 hydrogens, but sodium only grabs 1 chlorine?
Ah, now you're asking about their combining power. That's valency.
Valency. I remember that term. Can you give us a simple way to think about it for listeners who might be a bit rusty on their chemistry?
Think of it like connection points, or maybe hooks. Valency is basically the number of hooks an atom has available to link up with other atoms.
So oxygen has a valency of 2, meaning it has 2 hooks to grab hydrogen atoms, which each have a valency of 1.
Exactly. Knowing the valency is key to figuring out the correct formula for a compound.
Right. And when we just combine 2 different kinds of elements, what's that called?
Those are called binary compounds, like sodium chloride, NaCl, or our water example, H2O. Just 2 types of elements involved.
And there are rules for writing the formulas, right?
Yeah.
UPSC rules.
Oh, yes. Very clear rules. For instance, when you have a compound made of a metal and a nonmetal.
Like salt, sodium metal, and chlorine nonmetal.
Precisely. The rule is you always write the symbol for the metal first.
Metal first, so NaCl, not ClLna.
Correct. And then the valencies often dictate the subscripts, the little numbers. Like for magnesium chloride, magnesium Mg has a valency of 2 plus lime chlorine, Cl, has a valency of 1 zinc. To balance the charges, you need 2 chlorines for every 1 magnesium.
So the formula becomes
MgCl. The valencies kind of crisscross to give you the subscripts needed for a neutral compound.
MgCl arrow. Got it. What about more complex things like ions, charged particles?
Right. Atoms can gain or lose electrons to become ions. A positively charged ion, one that has lost electrons, is always called a cation.
Cation. Positive. Like now.
Exactly. And sometimes whole groups of atoms can stick together and carry an overall charge. These are called polyatomic ions.
Polyatomic. Many atoms. I got it.
A common example is the ammonium ion, NH arrow, 4 hydrogens and 1 nitrogen acting as a single unit with a +1 charge.
NH arrow. Okay. And these polyatomic ions have valencies too.
They do. The sulfate ion, for example, is SOO, and its overall charge, its valency in compounds, is 2 times.
So,
Okay, so if you combine ammonium NH0 and sulfate, SOO, you'd need 2 ammoniums to balance 1 sulfate.
perfectly reasoned. So the formula for ammonium sulfate would be NHRO, SOR. You use parentheses to show the whole NHR unit is taken twice.
NH0. Right, the rules build up. Now, if we know the formula, like HRO or MgCl, can we calculate the mass of 1 unit of that compound?
Yes, absolutely. You just add up the atomic masses of all the atoms shown in the formula. That total mass is called the formula unit mass.
Formula unit mass. So let's loop back to our first example, water, HRO. We said hydrogen is 1U and oxygen is 16U.
Right.
So the formula unit mass, or molecular mass in this case for water, would be 2 hydrogens, so 2 times 1U.
Plus 1 oxygen, 1 times 16.
It gives us 2 plus 16 is 18U.
Exactly. The molecular mass of water is 18U.
And just one final check on ratios by mass. Our sources mention magnesium sulfide. What's the mass ratio there?
For magnesium sulfide, MgS, the atomic mass of magnesium, Mg, is about 24U, and sulfur S is about 32. So the ratio MgS by mass is 24.32. 24 to 32. Which simplifies. Downright divide both by 8.
Yep, that simplifies to 3.4. So in magnesium sulfide, magnesium and sulfur are always present in a ratio of 3.4 by mass. Proust's law in action again.
Wow, okay. We've covered a massive amount of ground here.
We really have. Think about the journey from ancient thinkers in India and Greece, just wondering about Parmanu and atoms.
All the way to Lavoisier and Proust nailing down fundamental laws about mass and proportions.
Which then let Dalton build that first proper atomic theory, connecting the philosophy to the measurements.
Then figuring out a universal language with symbols thanks to Berzelius and rules from IUPAC, setting a standard weight based on carbon-12.
And finally, using all that to understand how atoms combine, using valency to write formulas like MgCl or calculate masses. It's centuries of discovery packed together.
So what does this all mean for you listening? We now see that the chemistry you might have learned, all those seemingly rigid rules for names and formulas.
They aren't arbitrary at all. They're the hard-won results of centuries of debate, experiment, and brilliant thinking, all starting from that basic question. What happens if you keep cutting matter into smaller and smaller pieces?
And how do we prove those pieces behave predictably?
Right. It's a testament to the scientific method.
So here's a final provocative thought for you to chew on. We mentioned that Dalton's idea of a truly indivisible atom was later proven wrong. We found subatomic particles.
Science moves on.
Given that our current definition of atomic mass, the U, is rigidly tied to the carbon-12 isotope, a standard set back in 1961, what fundamental changes might happen in the future?
That's interesting.
As our ability to measure things gets even more precise, maybe down to the level of subatomic fluctuations or energy equivalents, could the definition of the atomic mass unit itself change?
Sure.
Could IUPAC 50 or 100 years from now decide carbon-12 is no longer the best standard? What might replace it?
A fascinating question. What foundational rule might need rewriting next, building on this incredible history we've just walked through?
Something to consider.